All right, problem 79. Problem 79 says a 200 gram, 40 centimeter diameter turntable rotates on a frictionless bearing at 60 revolutions per minute. So I'm going to draw this out. So we have a turntable is just a disc on its side, rotating about its center. Omega initial is equal to 60 revolutions per minute. And it's 200 grams, so it has a mass of 200 grams. And it's a 40 centimeter diameter, but we don't care about diameter. We're going to make the radius, which is 20 centimeters, but I'm going to write that as 0.20 meters because we want to do everything in standard units. Then it says a 20 gram block sits at the center of the turntable. So there's a block here, right here, with a mass equal to 20 grams or 0.020 kilograms. Remember, this is equal to 0.200 kilograms up here. That's sitting at the center turntable. A compressed spring shoots the block radially outward along a frictionless groove in the surface of the turntable. What is the turntable's rotation and angular velocity when the block reaches the outer edge? So the turntable is spinning like this, but while it's spinning, this block is going to be shot to the outside and it's going to end up out here. That's going to change the moment of inertia of the system, but the angular momentum will be conserved because we're not adding any torque to the system. So we're going to do this as angular momentum initial is equal to angular momentum final. Now the initial angular momentum is the angular momentum of the disc plus the angular momentum of the block, but the block is sitting at the center and we're going to treat it as a point source, so its radius is 0, so it has no angular momentum to begin with. So really we have I disc times omega initial is the angular momentum to begin with. Now the angular momentum final is going to be equal to the disc times its final omega plus the angular momentum of the point source, which is MVR. But we don't know what omega, we want this to be in terms of omega. Remember, V is equal to omega final times R. So we're going to just rewrite this. This becomes ID omega initial is equal to ID omega final plus M. And so V, I'm going to put in omega final times R, but R times R becomes R squared. All right, or we could write it like this. Omega initial is equal to, notice there's omega final, we're going to take out omega final, this becomes I of the disc plus MR squared, plus MR squared is what the I of a point source is. Okay, so you could have kind of write directly to this point if you would recognize that right away. We're going to solve it for omega final because that's what we want to find out, is what the final is. And so we're going to have the I the disc over I of the disc plus the mass of the weight times the radius squared. All right, but I, it's a disc, so this is 1/2 times M, and that's the turntable, times its radius squared over 1/2 the mass of the turntable times the radius squared plus the mass of the weight times the radius squared. Notice the radius squared can be canceled out. So the omega final, and don't lose omega initial up here, is going to be equal to 1/2 the mass of the turntable over 1/2 the mass of the turntable plus the mass of the weight, all times omega initial. And when you plug all the numbers in for that, you get that the final is 5.23 radians per second. Now what I didn't do up here is, remember, you had to convert this from revolutions per minute into radians per second. So I put a minute up here, I put 60 seconds down here, and I put 1 revolution here and 2 pi up here. So you multiply by 2 pi, divide by 60, and I get that this is 6.28 radians per second. So what happened is it went from this speed to this speed. So it slowed down when you move this weight from the inside to the outside. Now be careful here. angular momentum was conserved, but energy was not conserved. Because we added energy because the spring launched this out from here, so the energy came from the spring. So you can't say that energy was conserved. You can only say that the angular momentum was conserved. That's the answer for number 79. I shouldn't finish there. I should say if you convert it back, because I think that's what they wanted, you end up with 50 revolutions per minute. I think they want it in revolution per minute because they started in revolutions per minute.